In this lecture, we will learn about the electrostatic spraying of ultra high molecular weight polyethylene. It is a MWPE. It is ultra high molecular weight polyethylene. Which has been reinforced with hydroxyapatite and carbon nanotube. So, we are in this particular lecture, we will learn about the coating technique of electrostatic spraying utilizing this ultra high molecular weight polyethylene, which has been reinforced with hydroxyapatite and carbon nanotube to form a particular biocomposite. So, in this particular process, we will focus on what is electrostatic spraying and how it has been utilized to create a biocomposite coating. In this electrostatic spraying, we apply a very high voltage, which is the order of 40 to 100 kV, which is concentrated at the nozzle, and that has been obtained maintained at optimum voltage. Here, our the overall important criteria or the vital component of here is that we can attain highly charged powder particles. So, the powder itself has to be much more insulating in nature, so that charge can be created on the particular powder particle when it is passing through the particular nozzle, which is being maintained at certain high voltage. So, after that, what happens here is that non-charged powder particles, they do not adhere to the object because they can dissipate the charge very easily. So, in this particular case, we need some powder particles which can get charged, and that charge is being created by the voltage which is again concentrated at the nozzle. And once we can do that, we can coat the we can let the powder adhere to a particular substrate, and the powder which is going outside, which is not really sitting on the substrate while the process is going on, that extra powder can be recycled back to the powder hopper, and from there we can again circulate the powder. What is the overall working and how the overall functionality of this electrostatic spraying occurs? We will come back to it. It is more like a coating technique, the way we utilize it for spraying. So, we have a particular charged entity. We basically throw the powder at a particular substrate, which is kept at a little lower or the ground potential to complete the overall circuit, and the charge between the powder particles is utilized for the travel of those powder particles from a electrostatic gun to the substrate, and later on we can do some sort of a curing to keep those powder particles intact or so that they can get fused together. And again, it can be it is usable for all types of powders, and more than that, we can also utilize this particular powder utilizing the electrostatic spraying to coat either iron, steel, aluminium, titanium, etc. And as we know that there are certain common for the implant material, we need a particular implant material to be good enough in terms of strength, and hence metallic materials come as the emerging candidates for them. So, either we have stainless steel or titanium, 6 aluminum, 4 vanadium or cobalt chromium alloys, and we also saw some other elements such as certain other materials such as tantalum or even magnesium and many others. So, all those are nothing but metallic materials. So, this process can be highly utilized in terms of coating all those metallic implants. Again, it has a very simple setup, and it is again very fast and environment friendly. So, we see in this particular electrostatic spraying is that we can maintain a high voltage near the nozzle, and that particular voltage is utilized for creating a charge on a particular powder particle, and then we let this powder particle flow through and get deposited on a substrate, and then we can do some sort of a secondary treatment which can be basically the melting of those powder particles to get cured on a particular substrate, and the powder which is extra, which is kind of overspraying, that can be recycled again in the later stage. And again, the advantage of this particular process is that we can easily coat a particular metallic implant using any type of a powder particle which can get charged, and it is again a very simple setup, and it is very fast, it is very rapid, very simple process, very rapid process. At the same time, it is environmental friendly because it is not generating any fumes. So, this is the overall setup of electrostatic spraying. How does it really appear is that we apply certain particular voltage. We have a container which contains our powders. So, we have our powder particles out here. Then we have this electrode which is kept at a higher voltage, and then we have a substrate on which we want to coat this particular powder particles. So, we have a particular electrode. As powders are passing through it, they get charged. So once a charge is being created on the powder particle, so right now it is at higher potential, and then basically it progresses to the lower potential side, and we can have some fans or blowers which can allow the particles to retain certain velocity, or basically to flow from gun to the substrate. So that is the overall philosophy out here, that we apply a particular blower, it carries away the powder particles, and once it is carrying over the powder particles, it will encounter electrode which is centrally located in the gun, and that makes the powder particles to get charged, and the flow of air which is being blown from another end, it carries away the powder particles, and now the powder particles are charged in nature, and once they strike the substrate, they can transfer the charge back to the substrate. But in the particular process, what is happening is all the powder particles they have similar charges. So there is some sort of a electrostatic repulsion, and that electrostatic repulsion is the cause of uniform dispersion of the powder particles. So that's what happens in the conventional electrostatic charging system. Again, so this is overall, it is one of the very simple processes, as we see here, that we apply certain voltage out here, and then that voltage is being carried over by the electrode, which is facing the front portion of the, this is nothing but the electrostatic spraying gun, and that blower is creating, is allowing the powder particles to flow, and as soon as they are flowing, it is getting charged because it comes and interacts with the electrode, and once it strikes a particular substrate, the overall repulsion between the powder particles, because of the similar charges, creates a very nicely dispersed powder particles sitting on the substrate, and once we have this powder particle sitting on the substrate, it is just sitting, it has not formed a coating or anything like that, it is just sitting on the substrate. So in the process, we don't have to damage it, we don't have to damage the overall orientation of this powder particles, or the we should not tap it, otherwise it will lose its overall integrity, and then later on we can take the similar plate or the substrate and get it cured at much higher temperature, which is to be above the melting point of the particular polymer which has been sprayed onto the substrate. So we take all those deposited powder particles which are now very nicely dispersed, but they are just hanging on mechanically. There is no metallurgical bonding or there is no fusion between the powder particles, so they are just sitting mechanically on a particular substrate, and later on they have to be taken to the oven and then cured. That is what is happening in the conventional electrostatic charging system. But when there are certain crevices, and we say if we had a particular implant, substrate which has a certain cavity or some sort of a cage effect. So in this case, what happens? As soon as powder particles they start depositing on the front portion of that, and they have now charge. They are now the charge entities. And the second powder particle, instead of getting inside this particular cage, it will experience a repulsion from the already deposited powder particle. So it will tend to find a new site for its deposition, and it can find an easy path of travel on the surface of this particular substrate, not inside of it. So in that particular sense, the powder particles which are now charged, they will try to go and sit on the top surface rather than the inside surface, and if we want to coat the particular substrate from the inside as well, that becomes very difficult. Initially few powder particles can go inside, that will be fine, but as soon as we experience more and more charge which is depositing on the particular front portion of that particular substrate, it will be very difficult for the powder particles to squeeze through it and then get deposited inside as well to a larger extent. So that is called a Faraday cage effect, and that can create difficulty in the coating of a particular powder. So our overall aim is to create a biocomposite which need to have enhanced mechanical property, because if you are creating a particular biocomposite, we need it to perform much superior to already existing coating materials. So if it is a polymer, we definitely want it to have a higher wear resistance as well as higher scratch resistance, and if possible, we would also want to extend these developed materials as a real life orthopedic implants. So we also need some sort of a studies, in vitro and in vivo studies, for the confirmation of the biocompatibility or cytocompatibility of these particular coatings. And as we have seen in the earlier lectures, that surface is one of the very critical components of deciding the cytocompatibility, because any particular environment will come in contact with the surface first. So that is the critical issue in terms of deciding the cytocompatibility, and if these coatings, they have to be utilized as a superior mechanically, which are much more superior in terms of the mechanical and tribological properties. They also have to retain the cytocompatibility at the same time. So that then only we can extend them to certain potential biomedical applications. So there are certain attributes to it. First of all, we are utilizing this electrostatic spraying for the powder coating. Secondly, we know that they need some charge for some surface so that they can dissipate their charge. So for that, we need to have a metallic entity where the charges can be taken away. That is nothing but a metallic substrate, which can be titanium alloy, it can be stainless steel, it can be cobalt chromium alloys. The only required criteria is that the substrate has to be conducting in nature. Once we have that, we can either utilize low density polyethylene or ultra high molecular weight polyethylene as the main component of the coating. So we are going to deposit a coating which is rich in polyethylene. It can be ultra high molecular weight or it can be low density polyethylene, and we can make that as a major constituent of the coating. And because these coatings are very softer in nature, we also want to increase their wear resistance or the tribological properties. So for that, we can either introduce something called a hydroxyapatite. We can also induce some ceramics, it can be aluminum oxide, or we can also incorporate carbon nanotubes for improving the strength as well as stiffness. So once we have much superior mechanical properties, automatically we can expect that the wear or the tribological properties will also enhance with the particular reinforcement. And again, we in this particular much better because of its superior corrosion resistance as well as its toughness. So once we can select a very appropriate biomaterial, we can always do some sort of a coating which can be of polyethylene, which is again still biocompatible material, and we can enhance its strength by using certain reinforcements such as hydroxyapatite or alumina or carbon nanotube. And again, their incorporation will depend or will vary depending on what kind of applications we are aiming at. So we know that for the polyethylene matrix, conventionally the polyethylene has shown to be excellent or exceptional in terms of biocompatibility, such as total hip replacements. So in THR surgeries, polyethylene has to be shown to be exceptional material or the very excellent biocompatible material in terms of total hip replacement. But the problem with this is that polyethylene, it can degrade over time. So that might create some bone loss or maybe hip implant loosening, because once we are losing some material, it always creates some gaps or some spaces between the implant and the bone. So for that, we want the polyethylene coating to survive much longer or for a very long time. Generally, we have a ceramic balls and a polymer liner, then it will always lead to much more degradation of the polymer coating. So if you want to improve the wear resistance or the tribological properties of this polyethylene, we need to always incorporate with certain ceramics as a reinforcement. So in this particular case, we also want to we may want to create some sort of a porous coating so that cells can really come and adhere, or depending on the kind of applicability, we can also provide some lubrication in the particular porous coating. So that is the deal with this particular polyethylene matrix. At the same time, polyethylene can also allow for the tissue attachment or the biological fixation. So that is one more advantage of the polyethylene, is that it can allow biological fixation and it can allow tissues and cells to grow onto its surface. So in this particular component, we are utilizing ultra molecular polyethylene because it has shown to be exceptionally cytocompatible in total hip replacements, and it is a very commonly used bioinert material for implants. But the problem with this polyethylene is it is limited to only soft tissues. Because of its lower mechanical properties, it is limited to only soft tissue implants, and at the same time it is very low elastic modulus and low yield strength. So to improve those particular properties in terms of strength as well as wear or tribological properties, we may want to add some hydroxyapatite. And hydroxyapatite, it has shown to be exceptionally bioactive material. It has a close resemblance to bone and teeth because its calcium to phosphate ratio is 1.67, and because of its bioactive nature, it also supports bone growth. So in certain cases, when we want the bones to get reattached to the implant material and to provide a strong reinforcement, hydroxyapatite come to our rescue. So again, it leads to the bone resorption and implant loosening in case we get a very poor crystallinity or generation of some secondary phases which are amorphous in nature, So that can also create certain some problems in case the processing is not done properly. So a session has already been taken in terms of the overall processing of this bioceramics or the or even the bioglass materials. Coming next, and if you want to improve the fracture toughness or the strength of the polymeric materials, we may also want to introduce some carbon nanotubes as a reinforcement, because its fracture strength is 200 gigapascals. It's one of the stiffest material with a Young's modulus of 1 terapascal. It is approximately 6 to 10 times as strong as steel, but at the same time it is as light as 4 to 6 times lighter than that of a than a steel. So that is how it can provide exceptionally toughening properties. So if we are able to reinforce it in polyethylene matrix, it can result improved fracture toughness. It will also induce improved strength. It will also improve wear resistance improvement by approximately 1.5 times. So we can see such things have been already reported with the incorporation of carbon nanotubes. So one more problem out here we see is that our cortical bone it has elastic modulus of from 7 to 30, and strength is approximately 50 to 150 MPa. Its fracture strength is only 1 to 3%. So if you want to match it with polyethylene has a modulus of around 1.25. Its density also is very similar to that of a cortical bone. It is approximately 1. Its strength, hardness is around approximately 104, which falls in range. It has a very high fracture strain as we want to require, as we might require. And if we can see, if we can start introducing some sort of a hydroxyapatite in terms of volume percent, or we start introducing some sort of a carbon nanotube, we are seeing improvement in the mechanical properties in terms of its modulus, and that thing is now coming back into the regime of the modulus as that of a cortical bone. So what happens is low density like ultramolecular polyethylene is it can start matching the modulus of that of a bone once we start reinforcing it with certain ceramics. So that is the advantage it can provide. It is very light. Polyethylene is very light, so it can soon reach the density of a bone, approximately 1 grams per cc. And whereas our hydroxyapatite or alumina itself, they are much more, they have very high stiffness. So what happens with them is there is some sort of a bone resorption, because the body starts thinking that the overall load is being borne by the ceramics such as hydroxyapatite or alumina, monolithic alumina and hydroxyapatite, once we only have that as an implant. So bone starts thinking, oh, they are not really needed there, and because of aseptic loosening we can also see some absorption of the bone itself, because the overall load is being borne by some other material. So that can be a problem. That is the reason our polymer matrix can come to our rescue in that particular sense, that it has a lower modulus and it can match the elastic modulus as well as the strength, as well as it can have a very superior fracture strain as well. That gives the overall importance to the ultra high molecular polyethylene, which is being reinforced with hydroxyapatite as well as carbon nanotube. So from the scanning electron microscopy, we can see that how the powders are being generated. Like we can see some powder particles which are approximately around 20 microns or so. We can see the micron bar here, so around 10 to 20 microns in diameter. And then we can also start reinforcing them with some carbon nanotubes. All those carbon nanotubes appear as small tubular structures, which we can see out here, and that thing has to be also dispersed, because the carbon nanotubes can provide much more strengthening only once they are distributed throughout the matrix. If they are isolated in some certain location, that particular regime can become much more stronger. And also depending on if they are not strong, if they are not dispersed properly, one region will become very weak. So it will also lead to some sort of a straining or some sort of a stress concentration at certain locations. So that might again be a problem. Again, people do not know how CNTs or the carbon nanotubes will react once they are in the body environment. So there have been generally two schools of thoughts. On one hand, carbon nanotube, it is nano in nature, so it can penetrate through cell walls, it can create some damage, or it can get agglomerated, it can basically get accumulated either at liver or brain or even heart or some other location. So that can even create some problem. And even once anything is a nano form, and if it goes to our lungs, it is very hard for us to take it out. So it can be very toxic, depending on how the CNTs are being now introduced into the matrix. But on the other hand, our body is also made up of carbon. So why carbon will be deleterious to our own body? So there are two schools of thoughts which are being proposed by the researchers, and once we can trap all those CNTs in some matrix, then we don't allow any free CNTs or any loose CNTs to flow in our blood, or don't allow them to flow through and get accumulated at certain parts of our organ or the organ of the body. So we want to, once we trap the carbon nanotubes, we can get much more strengthening in the polymer matrix, and we can also achieve much more superior mechanical properties while retaining the cytocompatibility. So in this particular case, we have utilized ultra molecular polyethylene, and then carbon nanotube powder, carbon nanotube is now being dispersed into the matrix by a certain ball milling technique, and once we have that, we can utilize the electrostatic spraying to basically coat the substrate material, and the overspray, like once we are spraying it, some part of it can also go outside the particular substrate regime. So once we have substrate like this and we start coating using a particular gun, once we are coating it, the powder particles may sit onto it, but some of it can also go outside the particular substrate where we are spraying. So this extra powder particle, the extra regime of the powder, it can be again collected back. If we have a particular container, we can again collect this particular extra powder back and we can recycle it. So we can minimize the overspray, and we can again minimize the material loss, and we can, and in this particular case we are utilizing titanium substrate. So once we have this particular coating which is deposited onto the titanium substrate, we take this deposited layer and then we heat it in an oven for around 180 degrees centigrade depending on the melting point of the polymer. So we want the polymer to melt on the substrate so that it can get fused and it can melt and basically coat the titanium implant. And depending on that, we can also have a certain temperature as well as certain time, like in this case we utilize 30 to 40 minutes. So we can decide the temperature and time depending on the particular polymer which we are utilizing for the electrostatic spray. So what we are doing, we are taking titanium substrate, we are electrostatically spraying the ultra molecular polyethylene, which is now reinforced with carbon nanotube. And once we have that, we put it in an oven for a certain duration of time and temperature to basically cure the polymer and achieve a uniform coating on a titanium substrate. And because in this particular case the melting point of polyethylene is around 136 degrees centigrade, but it is very viscous at this particular temperature. So when we want the polyethylene to flow, we need to obviously heat it to superheat it to much higher temperature than 136 degrees centigrade. So in this particular case we are heating it to around 180 degrees centigrade, so that now it is fluid enough to cover the overall surface of the titanium substrate. So that is the overall deal with the deposition of CNT reinforced polyethylene using electrostatic spraying. And once we fracture those samples, in this case when we have only polyethylene, and in second case once we are reinforcing it with some carbon nanotube. So what we can see here is, in this particular case, once we have only polyethylene, nothing else, no CNT, we are seeing a very flat morphology. But once we have some carbon nanotube, we can see all those very dimple kind of a very fibrous kind of a fracture out here. So in this case it is very fibrous, in this case it is a very flat fracture. This directly tells that my coating or my particular coating which is now reinforced with carbon nanotube is much more ductile. So that's what is giving me much more advantage, that I can have a very adherent coating, very nice coating, and that is also have much more higher fracture toughness. At the same time it should show a very good mechanical properties, because what is happening here is we want the surface to yield once it is undergoing some stresses. So in that particular case we can see that with CNT I am getting much more fibrous coating which can basically shear off or deform with particular applied load, and it can sustain much longer time. So that is the advantage with the addition of carbon nanotube, because carbon nanotube, it has exceptional mechanical properties, Young's modulus of around 1 terapascals, fracture strength of around 200 gigapascals. So that is the advantage of utilizing carbon nanotube as a reinforcement. At the same time, it is also assisting formation of a fibrous structure, and which is much more, which can provide us much more stress absorption in many cases. This is how the coatings look like. In this case, we utilize only polyethylene with some carbon nanotube. So in this case, we have ultra molecular polyethylene, and we have around 5-8% of multi-walled carbon nanotube, and the coatings, they show a very smooth surface finish, as we see here. And in this case, because of CNT, we are seeing a little grayish coating, and these coatings are now electrostatically sprayed on the steel substrate. In this case, we utilize a steel substrate, not really titanium substrate, but we can see the overall feel of how the coatings are deposited using electrostatic spraying. And correspondingly, as we have seen, the fracture part was very different. So in this particular case, with the reinforcement of the 5-8% multi-wall carbon nanotubes, we are seeing increase in the elastic modulus by approximately 10%. That is again very substantial, because we are using only 5-8% of CNTs, and that is enhancing the mechanical properties or the elastic modulus by around 10%. At the same time, we can also see improvement in the hardness. This is very marginal, but at the same time, we can see there is overall generic increase in terms of general increase in either the hardness as well as the elastic modulus too, marginally, but we can see there is some sort of a influence of carbon nanotube reinforcement in the ultra high molecular weight polyethylene matrix. So that is what we can see, that electrostatic spraying coatings, they are very smooth, so we can utilize them as such, because they are very smooth, surface, and aesthetically also they look very good. So we can utilize all these coatings as such and in the implant, while they are showing the improvement in the mechanical properties. Now coming next, we can see that in the second case, we have some ultra molecular weight polyethylene with hydroxyapatite coating. So in this particular case, we have a titanium 6 aluminum 4 mm substrate, and over that we have electrostatically sprayed this particular coating, which is ultra high molecular weight polyethylene, which is now reinforced with some hydroxyapatite. And we can see one very nice observation, that the coating is very uniform. This particular coating, it is very uniform. The interface is very adherent. We can see out here, there is no cracking. We can see no cracking at the interface. So we can see the interface is very strong, which is between the substrate and the coating. And later on, this particular part was sectioned and mounted. So we have this epoxy mount, which is basically captured the coating as well as the substrate. So we can see in this case, the coatings are very uniform, which is approximately 40 to 50 micrometers thick. But main part is, it is very uniform. We can see this particular part, that we can achieve approximately a constant thickness or a very smooth surface utilizing this electrostatic spraying. So that is the basic advantage of electrostatic spraying, is I can achieve very uniform coatings on a metallic substrate. And mostly all our implants are metallic in nature, because they need to render enhanced fracture toughness, enhanced fatigue life, and such. Basically, they have to take care of the wear and tear and work as a horse material or the workhorse material. So in that particular case, this particular process can highly be utilized for electrostatic spraying of certain polymer coatings. So that part we can see here, that we can achieve a very nice uniform coating on a metallic substrate, which is titanium 6 aluminum 4 1mm substrate, and I can achieve good interface. So I have very good interface without any cracking. Coating is highly adherent coating. And third thing is, I am achieving a very uniform coating thickness. So these are three very nice components, which we can really see here, that I have a very good interface, coating is highly adherent, it is not peeling off, and I have a uniform coating thickness. So in that particular manner, I can really see how much coating I really require out here. But one problem with this electrostatic spraying is, I cannot achieve very high coating thickness, which can exceed say 200-300 microns or so, because my substrate needs to be very highly conducting. Once I achieve a certain thickness of this powder, later on it is very hard for me to keep developing powders on a charged surface, because I have powder once we melt it becomes insulating, and powder themselves have some charge, so it will not allow charge to keep accumulating with the electrostatic spraying. So I keep the substrate, I deposit certain thickness of powders. It is not limitless. The process is not limitless. I can achieve only very fine coatings, which can be limited up to say around 150 to 200 microns and not more. That is a disadvantage of the process, but it becomes advantage for this particular as a biocompatible coating, because we can achieve very fine, adherent and uniform coating on a particular metallic substrate. So seeing overall feel of it is that in first step is the processing of this ultra molecular weight polyethylene, which is now reinforced with hydroxyapatite and carbon nanotube, and then Once we have synthesized those coatings, we need to have some sort of a biocompatibility test, in vitro biocompatibility, that can come from either cell culture or bacterial culture studies. Once we have done that, we will know what are the potential materials and for which we can expect much more enhancement in the mechanical properties. So for that we can either do nano scratching, we can do fretting, we can also do ballpoint pin desk. And once we attain that, once we can see how we are getting the enhancement of the mechanical properties, we can come to the optimization. We can come to the process optimization by electrostatic spraying in terms of hydroxyapatite content, in terms of any other reinforcement what we require. And some other component which might be essential is what might be happening with the either CNT HAP interface or the polyethylene HAP interface or the polyethylene CNT interface. So there can be certain components which can be answered via some computational modeling. At the same time, once we have confirmed from in vitro, from mechanical properties, from the optimization of the composition, we would also want to know what is happening in vivo in terms of both long term and the short term test. So that part also is that part also might become very critical in terms of evincing the overall biocompatibility of polyethylene, which is now reinforced with hydroxyapatite and carbon nanotube. So in this particular case, we can see overall pyramid of this CNT reinforced ultramolecular polyethylene with hydroxyapatite. So there are certain criteria to it. First thing is the nanocomposite processing. So we have to optimize the process and then synthesize a particular coating or do the spraying part. Then second part is the mechanical properties. So we would want to know what is happening in vitro and in vivo, and also design what is happening to the wear or the tribology of this particular coating, and then so we can finally select the coating. And further we would also want to know what is the overall effect of the composition in terms of how the reinforcement is being given by either hydroxyapatite or carbon nanotube, how those phases are distributed. So microstructurally also we need to basically reinforce what we really are planning to look at in terms of their distribution, how the phases are now being distributed, both hydroxyapatite as well as carbon nanotube in the polyethylene matrix. Then at the same time, what is happening between the interfaces of all those? It can be hydroxyapatite and carbon nanotube. It can be polyethylene plus hydroxyapatite. It can be polyethylene plus carbon nanotube. So there are certain areas where we would want to look at the overall interfacial compatibility. So this forms the overall pyramid of processing. How do we process it using electrostatic spraying and be able to optimize the composition, or first the process, then the composition, and then once we optimize the composition, we would want to look at the mechanical properties. So what is happening at the interfaces, how the phases are now being distributed, and then coming on to the in vitro and in vivo testing, so that we can choose them as a potential biomaterials. So this is the overall strategy of developing ultra molecular polyethylene, which is now reinforced with hydroxyapatite and carbon nanotube. So we can see how this electrostatic spraying can allow us to do this particular type of processing, and how we can select in terms of the process. How do we optimize the process in terms of its duration or the time? What is the overall composition of hydroxyapatite will be utilizing in polyethylene matrix? What is the composition of CNT will be utilizing in reinforcing the polyethylene? Then what is the enhancement and mechanical properties we are attaining by this particular reinforcement? Then how the things will behave at the interface, and how it will eventually lead to the overall cytocompatibility both in vitro as well as in vivo, to finally come up with the potential biomaterial which is now reinforced with both hydroxyapatite as well as carbon nanotube. So that is the overall scientific processing structure property correlationship which becomes essential. So that is the overall deal with the development of ultramolecular polyethylene with hydroxyapatite and carbon nanotube. And most importantly, interfacial wear is also one of the very critical components, because once we have surface 1 and surface 2, how do they interact? How is the overall roughness? How is the overall chemistry? How is the overall lubrication between the two surfaces will result how my material will now be lost once I have two operating surfaces. So I can have a dry friction once I don't have any particular fluid, or secondly I can also have a wet or lubricated friction. So in this particular case I have some hydrostatic film which can form between the two surfaces, and once I have some film forming between those two, it is now only the film which can easily shear off, and once it is now shearing off, I will achieve very low coefficient of friction because the surfaces will flow very smoothly over one another. Whereas in case of dry friction, I don't have any sort of a lubrication. that's how the porosity also comes into picture, that once I have my surface are very dry, it will always will have some ridges and grooves, because any surface is not flat, atomically flat. So that's how it will lead to some sort of contact between the asperities. Once the asperities are in terms of they have length of microns to nanometers, it will always lead to some sort of a friction between those two surfaces. And once I have certain friction, it will interlock all those asperities, and with a particular movement, it will start breaking off all those asperities. So eventually, I would want to introduce some sort of a lubricant to avoid this friction, and so that the surfaces can flow very smoothly over one another. In this particular essence now, when I can see I have much more easier shear, so I can introduce some carbon nanotube, or I can introduce some ceramic particles, so my wear basically goes down to a very large extent. So once I have carbon nanotubes or hydroxyapatite is a ceramic in nature. So the abrasion on once I have a hydroxyapatite reinforcement, it will always be much more superior to that of a polyethylene alone. Again, it also depends on the interfaces. If I have a very poor interface between hydroxyapatite and polyethylene, then hydroxyapatite can also come out, and it can also start eating away my polyethylene. So I need to have a very strong interface between polyethylene and hydroxyapatite. CNTs on the other hand, they are much more graphitic, and graphite is also used as a lubricant. So depending on how the interface is between CNT and hydroxyapatite and polyethylene, I can somehow control my wear or the tribological properties. So at the same time, I can also provide some sort of a lubrication at the contact surfaces to decide the overall wear of a particular interface. So we can see how the composition itself can be much more influential in terms of dictating the overall wear between the two compositions. In this case, we will see that we have done a nano scratching of ultra molecular weight polyethylene, which is now reinforced with hydroxyapatite and carbon nanotube. So in this first case, we only have polyethylene. In second case, we have reinforcement of some hydroxyapatite. So what we can see here is that I have a nano tip. Then what I am seeing here is the wear volume, which is now calculated by the amount of or the volume of material being displaced by the indented tip, both in polyethylene as well as in the which is now being reinforced with the hydroxyapatite. So we can see I have certain wear volume in polyethylene, but once I am reinforcing with some ceramic, I am getting much higher wear volume. That is much more contradictory, because once I am reinforcing my polyethylene with certain ceramic, I will expect the wear volume to go down. But what is happening here is that the interface between hydroxyapatite and polyethylene may not be that good. So what is happening is hydroxyapatite probably loosening away, and that again is acting as a scratching media for the polyethylene. That is the reason I am seeing much more or much higher wear volume once I am reinforcing with hydroxyapatite. But once I start introducing some carbon nanotube in terms like 2 weight% and 4 weight%, I am seeing much reduction in the wear volume. This is happening because carbon nanotube, they have very superior mechanical properties. Also, they also serve as a lubricant. They have exceptionally superior wear properties, tribological properties, mechanical properties. At the same time, they have much more lubricating properties. So once I am introducing more carbon nanotubes out here, I am seeing a overall reduction in the wear volume. It means I am achieving a superior wear resistance in the CNT reinforced hydroxyapatite, which is now again reinforced in the polyethylene matrix. So once I am increasing the CNT content, I am seeing further decrease in the wear volume. It means I am achieving much more superior tribological properties once I have CNT reinforced or enhanced CNT reinforcement in the polyethylene and hydroxyapatite matrix. That is what we can see, that once we have a poor interface between hydroxyapatite and polyethylene, I am seeing much enhancement in the wear volume, or my wear resistance is now dropping off. But once I start reinforcing with carbon nanotube, I am seeing much more enhancement in the wear resistance. That is what is happening out here. So my wear volume is basically going down with the increased CNT content, and that is what happening is with the nano scratching out here in the particular case. At the same time, I can see with the increase in the hydroxyapatite, I am seeing increase in the Vickers hardness. That what can be expected, because hydroxyapatite is ceramic. So once I am adding some ceramic, obviously my hardness should go up. And further increase in the carbon nanotube, I am seeing much little marginal increase in the hardness as well. So we can see here is that wear volume is decreasing with increasing CNT content. So obviously my CNT is now improving the wear resistance. once I am saying that CNT is a lubricant, I should expect that my coefficient of friction should go down. But we are seeing exactly opposite. In this particular case, we are seeing coefficient of friction is now going up with the CNT content. So with CNT content, I am seeing my increase in the coefficient of friction. And first of all, I had polyethylene; it was showing me some coefficient of friction. Once I am adding hydroxyapatite, I am seeing decrease in the coefficient of friction. That is happening because at nano level, once I am doing a nano scratching, there is very poor interface between hydroxyapatite and polyethylene. So as soon as I am putting my indenter tip, it is very easy for the indenter tip to blow away the material on the side. So there is very less of a lateral force in comparison to the normal force. So that is the reason I am seeing much reduction in the coefficient of friction for the 5% hydroxyapatite. Whereas in case of once I am adding some carbon nanotube to it, what is happening here is now CNT is introducing much more strength to the polyethylene matrix. They have very superior mechanical properties. So indenter tip finds very difficult to displace the material. So at nano level, things are very different, and it finds harder to displace the material. So lateral force goes much higher. That is the reason we can see increase in the coefficient of friction once we have more CNT content. So it is in agreement with the observed wear resistance or the wear volume loss which was observed in the nano scratch testing. And finally, everything boils down to the how the cells or how the cytocompatibility of those particular material behave. So if once we take a control and once we take a polyethylene, we can see the number of cells how they basically grow. In this case, we have utilized SOS2 490 SOS2 cell line, which is a mouse fiber osteoblast, mouse fibroblast at a wavelength of 490 nanometer and at a 630 nanometer. And we can see the quantification wise is that we are seeing approximately similar cytocompatibility. So I can see that the overall count of the cells is through a particular quantification technique, it is coming out to be using a UV spectrophotometer. We can see that the particular counts are approximately similar. They are not deteriorating to a stronger extent. If I had a pure HAP or I had a polyethylene, I am seeing my CNT is approximately the same. Though I can see certain decrease in the cytocompatibility, but not to a very large extent. But my 2 weight % CNT, they are showing me much more superior properties as compared to the 4 weight % CNT. So overall, we can say that we can achieve some marginal improvement in the mechanical properties without deteriorating the cytocompatibility of this particular composite. So eventually, we can say that electrostatic spraying can be utilized because it is a particular process in which we utilize a blower to take the powder particles away, get them charged with the electrode. Once it is now charged with the electrode, it cannot disperse very uniformly on a particular substrate because of electrostatic repulsion between them. Once we have that particular entity, we can take it and we can cure it, and curing can be done at a temperature which is higher than the melting point. So we can achieve a little fluidity in the particular polymer material, so that it can spread out and it can coat the particular substrate nicely. And as we see that the surface was very adherent, it can cover the crevices very uniformly. It is adherent, it is not peeling off easily, and also it has a uniform thickness. That gives the advantage of the electrostatic spraying. And that was from the processing part. And now coming to the material part, we can utilize polyethylene very easily out here, and we can also incorporate some reinforcement, which can be ceramic reinforcement of hydroxyapatite, or it can again be carbon nanotube to provide some strengthening to it. We can also utilize some ceramic reinforcement such as aluminum oxide to incorporate much more wear resistance or the tribological resistance. And as we see, it also depends on the interfacial interaction in the interfacial component of the matrix as well as the reinforcement. If the reinforcement itself is not compatible with the matrix, it might just go out, and it can also serve as a agent to again scratch off the polyethylene surface, because hydroxyapatite it does not have a good interfacial bonding with the polyethylene. It can come out and create a 3-body wear. But once we also introduce some carbon nanotube into the material, carbon nanotube can also act as a strong reinforcement, and it can provide much more strengthening, much more fracture toughness, much more superior hardness. It can also have superior wear and tribological resistance. So that is the overall deal with it. Also playing with the composition part and how we can utilize them in terms of electrostatic spraying and depositing them onto a body implant surface. So that is what basically I'll summarize the lecture again. That electrostatic spraying, we are utilizing electrostatic gun which can carry the powders, which can form a very nice coating on a particular body implant material. The substrate has to be much more conducting in nature. So that is the overall limitation to it. At the same time, we can achieve very uniform coating, but we can't achieve very thick coatings using electrostatic spraying. And in this particular case, we are limited only to the certain polymers which can be easily deposited and which can be easily cured to give a uniform coating. And the coating size is also, thickness is also limited. So that is the drawback of this particular process. But again, it is advantageous to bio coatings or bio implant coatings, because those are very, very fine, and that is what we really seek for achieving a very good interfacial properties. So that is what it will assist us in terms of achieving. And once we have a very uniform and adherent coating, which is on the substrate very uniform, we can also expect the similar bio cytocompatible response from the surface, because surface is the one which comes in direct contact with the blood or in any particular biological environment. That is the advantage of that. And then we can see that using altering all these compositions, we can attain the required tribological properties, required biocytocompatible properties using this electrostatic spraying. So I'll end my lecture here. Thanks a lot.